Moving into section 2, we're going to have devices and IPs. This is one of the most important slides that you will need to memorize. We're going to talk about the model of the OSI. It stands for Open Systems Interconnect Model, and the TCP IP model. So right here, this is your OSI model. It is 7 layers, starting from physical, data, network, transport, session, presentation, and application. We're going to talk about all these different protocols that you can have within each model. And the other model you should know is the TCP IP model. It's basic 4 layers. And when we use the modeling schema for OSI or TCP IP, it's for us to provide a standard structure of how data is flowing from start to finish. And it's extremely helpful for understanding where your ones and zeros are within that transmission of communication, where you can troubleshoot, where you can apply different protocols at each layer to help the packets get pushed along. Remember, I said ones and zeros kind of get bumped into packets, and the packets traverse the cord or medium of a copper or fiber optic cords and kind of get reassembled. They do this through the help of a bunch of different protocols. So again, just wanted to make you aware of, if it's the first time you're hearing about important models, the OSI and TCP IP model, a great way, you're going to have to memorize this. I would definitely memorize everything that's on the slide. It's going to be extremely beneficial for you in your career. It's going to come up on exams, and you're going to use it throughout your career for basic troubleshooting or thinking about where the data might have been lost along its path. So if we just focus on the OSI model for this section, starting at the physical layer, this is your bits. So these are your ones and zeros. If you remember from mod 1, a bit is a 1 or 0. This is your physical layer. Think about bits. Think about your cables that we just talked about, Cat 4, 5, 6, 7, your fiber optic cables, your DSL lines, coax, etc. This is your physical layer. At layer 2, so this has 7 layers, and we count from the bottom up. So this is layer 1, this is layer 2, your data link layer. Your packets of your form of ones and zeros are now going to be bundled into something called frames. At layer 2, we think Ethernet, but I want you to think switches and MAC addresses. Those are the devices that we're going to talk about that relate to data as it transmits it from ones and zeros to the next step of preparing that for being sent is your data link, your switches, and your MAC addresses. Moving into layer 3, we have network. I want you to think of routers and IPs. For layer 3, your packets will change from a frame to actually a packet. I know I've been saying packet a lot, but packet is exclusive to layer 3. As you move up, it will move into the transport layer, and I want you to think TCP or UDP for the protocol that's going to transmit your packets over the wire. Now we call our packets segments. Layer 5 is going to be your session layer, and there are different protocols that you can use within the session layer to transmit your data through that session. 6, it's the presentation layer. How is that going to look? Is your data going to be encrypted? Is it going to be encoded? Is it going to be compressed? Are we doing any change to the presentation of our data as it's going through to the receiving end? And then at the top of the OSI model is our application layer. What layer of what application protocol are we using to move this data over? What kind of organization and structure can it follow based on this protocol to perform functions related to moving our ones and zeros? And when we talk about what the data is called from layer 5, 6, and 7, we're referring everything now to data. So the OSI model, you can, when you send data out, you're going from the bottom up to layer 7. And when you're receiving data, the data is coming to you and being stripped off at each layer, and it will work down the OSI model. We're going to talk a lot about this. We're going to reference the OSI model a ton, so I'm really not trying to drill too much information into you while being static on one slide. But if you can remember a good mnemonic for memorizing the OSI model, I would say we can do, please do not throw sausage pizza away. That is the mnemonic that I use to memorize the OSI model when I was first learning it. P for physical, D for data link, network transport, session, presentation, and then application. You would write out those first letters based on the phrase that you're going to remember the organizational structure in, and start answering your question on the exam that way. At a high level, I would definitely understand the order, the layers, what they're called. I would be aware of some of the protocols that we're going to discuss here, but just starting out on this slide, memorize your 7 layers, memorize what order they're in, be aware that on network, we're going to talk about routing and IP addresses. On data link, we're talking about switches and MAC addresses. We're going to get into these. And at the physical layer, we're talking about bits, so our ones and zeros, or our chords and mediums that are actually physical mediums that we're using to transmit our ones and zeros. That's probably all you need to know in this slide. We're going to continue to reference it throughout the course and throughout your career, and every other course that you probably take is going to mention the OSI model. Very quickly, moving into another major model to know is the TCP IP model. I just remember NITA. So it starts at the network interface level, your internet layer, your transport layer, and your application layer. Everything works the same. It's not just broken out into 4 layers instead of 7. Everything follows kind of the same structure for data being sent out, just a different model to explain data as it's being sent or received and the different steps that it takes along each layer of the model. Moving into network devices, just a few to make you aware of here. Starting with NICs, these are our network interface cards. So this example here is what a NIC would look like. This should look familiar as it is a Ethernet port. So we would plug in our RJ45 cable to this. It will have our twisted pair cabling within that cord, and we have the adapter on the end to be able to plug it in to be able to communicate ones and zeros with our computer. This is going to act as the interface between the computer and the network, allowing the computer to send and receive data across the network. So they can be wired, as in the form of an Ethernet cable, or it can be wireless if you have like an antenna that sticks out instead of an Ethernet cord to transmit a signal. And these are essential in every single computer or laptop that you buy. If you use Wi-Fi on your laptop and you don't use a cord, then you are using your Wi-Fi within your laptop through your NIC. Now, your laptop doesn't have an antenna that sticks out of it because we've come a long way in technology and we're very modern, and it's just built into your computer, and somewhere along the physical components of your computer, there is a signal that's coming out to allow you to have that signal to connect to your Wi-Fi at your home. So I just wanted to make you aware, a NIC, that's going to be that hardware component that gives you access to the internet, whether through a physical medium like Ethernet or over the air through Wi-Fi. Moving into another device you should be aware of is a switch. Again, we're thinking layer 2 of the OSI model, and whenever we think layer 2, we're thinking switches and MAC addresses. So what is a switch? It's a networking device that connects other devices together on a LAN. As we discovered, a LAN is just a local area network comprised of wherever you are local to that exchange of data. It's going to forward data between devices on the same network using the device's MAC address. I would definitely know what a MAC address is. We're going to cover that in depth later. It is a media access control address, and it's going to be something we call a physical address, and it's going to be unique to each device on the network or in the world, really. Each device has its own unique MAC address burned into the computer hardware components, and you cannot change the MAC address. It's a physical component within the device, and we're going to talk about it later. But it's going to improve network performances and reduce network congestion. The switch is going to change direction for all of the packets within your network to say, if I need to go from point A to point B, the switch will be in here to keep track of where I need to go in order to get to point B, so I don't get sent to C or D. The switch will say, based on protocols and routing, MAC addresses, MAC address of point A is trying to get to the MAC address of device B. I keep track of that in my table here. Let me route it appropriately. We'll come back to this. A router, now we're thinking layer 3 of the OSI model, which is network, and we're also thinking about IPs with routers. So a router is an example of what one looks like. In your home, you may have just a standing tower with a bunch of lights that come on for troubleshooting, or if it goes out, and out the back is your ports for Ethernet if you want to have a physical connection to it, and at the bottom you probably have your coax cable going out to a wall somewhere. This router is going to connect multiple devices on your network to the internet. As a basic example, in your home, the kind of symbol that we use to draw routers when we're just talking about it is just a circle with an X on it. So be familiar, if I'm going through the course and I'm talking about routers, it's going to be a circle with an X that just denotes a router, and a switch will just be, a square with a couple of lines in it to denote a switch, just so we can draw them out and talk about the concepts. But basically, if you had your home and you wanted to talk to another home through a WAN, you would go out, you would hit a bunch of routers through your packets until they are delivered across the correct route from point A to point B. It's going to forward data between networks based on the destination IP address, enabling communication between devices on different networks, and it's going to facilitate internet connectivity. So for here, think of switches, think of LANs, think of they have to be close, and they're going to use MAC addresses. And then for routers, think connecting devices over WANs, going to use IP addresses, and multiple routers can be involved, multiple switches can be involved. You can have a series of switches, a series of routers, etc. Just wanted to make you aware at a high level some of the devices you can have when it comes to networking, and these being kind of like the top 3. Taking what we just talked about with switches and MAC addresses and routers and IP addresses, it's very important to understand the terminology between a physical address and a logical address. I would expect this concept to show up on an exam. I would definitely know different terminologies here and have a strong understanding of the difference between a physical MAC address or something that's a logical address, which pretty much we're always talking an IP address. So starting with the MAC address, again, whenever you hear MAC, we're thinking layer 2 of the OSI, and we're thinking switches. This is a physical address, and it's a unique identifier assigned to the network interface controller, the NIC card that we talked about, by the manufacturer that made that interface card for the device or the access to the internet. It's used at the data link layer of the OSI model, so that's layer 2, and it's used to identify devices on a network. So this is just an image here showing a MAC address being present here, and it's showing like MAC ID and then a sequence of numbers, and it's going to be physically burned into this device, again through ones and zeros, on this card that's going to store the MAC address that is contained for the device. It's physical, and it's physically attached to the hardware component somewhere within your laptop, your computer, your iPhone. Anything that's a device that connects out to the internet is going to have a MAC address associated to it. We'll talk a little bit more about the details of the binary, bits information regarding MAC addresses and how they're structured. But right now, we're talking about the concept of a MAC address being something that is a unique address associated to each device that you've ever touched, ever, that connects out to the internet. Phones, tablets, computers, laptops, anything that has an ability to use Bluetooth, your IoT, your Internet of Things, everything will have a MAC address. and we want to think physical. When we move into a logical address, we're always going to associate IP. So we're thinking layer 3 of the OSI model, and we're thinking routers, and we're thinking IPs. An internet protocol address is a logical identifier assigned to each device connected to a network. IP addresses are used on the network layer of the OSI model and used to route data between devices on different networks. So if you have your laptop, it's going to have a physical MAC address that says it's unique to that specific physical device, and it's also going to have an IP address, which will identify it as a sequence of numbers to communicate when it gets up to layer 3 to a router where to route the data. So your MAC address will be useful to tell the switch where to route your data, and the IP will be helpful when it goes up the OSI model from layer 2 to layer 3 where to route your data. And these are the main components about addressing and how computers know where to send data from point A to point B. It goes up the OSI model. It follows different hardware and protocols at each layer to learn how to structure your data in your forms of ones and zeros to be sent across the network. We're going to talk a lot about MAC addresses and IPs, but just from this slide, know that a physical address, we're talking about a MAC address. And if you're talking about a logical address, you're talking about IP as your IP for your device. Maybe 192.168.1.0 today, but tomorrow it could become a different address. It could be 192.168.1.2 or another private IP, which we're also going to talk about, but it's not a permanent allocation like a MAC address is. Your MAC address for the device will never change, whereas your IP address for the device will change, it can change, and it may change very frequently. So it's logical. It's not static, it's changeable, it's dynamic, whereas your MAC address, static, physically burned into your computer in a very unique identifier. No one else is going to have the same MAC address as you, whereas other people, you can be sharing IP addresses if they're leased out to you from different days, so we think of them as logical. Let's dive into MAC addresses a little bit deeper. Again, whenever we think MAC, we're thinking layer 2 of the OSI, and we're thinking switches. Starting with the MAC address, this is a sample of a MAC address. I would definitely know that a MAC address is 48 bits long. So if we learned in Module 1 how to convert hexadecimal numbers to binary, you should be able to know how to convert A7 to the string of 8 bits within this group of pairing between the colons. So each of these will have 8 bits assigned to them if you were to convert them, 8, 16, 24, 32. So each one would have 8 bits, and if you have 6 spaces here, 8 times 6 gives you your 48-bit MAC address. Definitely memorize that. And what's really making up this MAC address here is your OUI and your vendor-assigned information. I know this breaks it out into the first couple of bits here contained within this 0 to have a broadcast and a local allocation, but for now, I want you to think of the first 3 parts. So the first 24 bits of the MAC address being your OUI. This is your organizational unique identifier, which will come from your vendor. So like Cisco will have their own OUI that will always be the same prefix of the MAC address for the same set of hexadecimal notation for your first 24 bits. So if Cisco MAC addresses always started with C810 Bravo Charlie, that would denote that this is a Cisco manufactured device, and then the other 24 bits is going to be your vendor assigned kind of unique identifier to your physical device. So a MAC address, it's physical, we're talking layer 2 with switches. Your switches are going to reference your MAC addresses from one device to the other, and it's 48 bits long, and at the front that identifies a unique identifier for you. Moving into IP, now we're thinking layer 3, we're thinking routers, we're thinking logical, and we're thinking, obviously, IP addresses. I would definitely know that an IP address is 32 bits, your MAC address is 48, and if we remember from Mod 1, converting decimal numbers into binary, so this was base 10 converting into base 2, you'll now be able to realize that each number will also have 8 bits assigned to it, and IP addresses will have 4 octets. So 8 times 4 is 32, and you can convert out your IP address into binary notation for ones and zeros. Again, logical, physical, 48 bits, 32 bits, routers and IPs, switches, and MAC addresses. So it's just a way for computers to be able to keep track of the data that they're sending as they move up the OSI model and add information to that packet of data to include additional routing information to get your data from point A to point B. So if you start at layer 1 with your ones and zeros, this will be transformed up at layer 2 to your 48-bit MAC address at layer 2. That will be encapsulated and added on the additional information of the IP address so that each device along the OSI model is adding additional information for how to route those ones and zeros according to the physical devices that are being used within transporting data. So it's just adding information on top to handle the routing process that takes place with your data. Talking about ARP and reverse ARP. So ARP stands for Address Resolution Protocol. It's used to map a device's IP address to its corresponding MAC address on a local network. When a device needs to communicate with another device on the network, it will send out an ARP request to obtain the MAC address of a device with the matching IP address. So me just doing a sample Wireshark capture here. We haven't talked about Wireshark yet, but Wireshark is a network protocol analyzer tool that you can capture packets going across your network and then filter down on the traffic and see what protocols are in place. And I just did a simple capture on my home network to say, show me the ARP traffic. So my device had gone out and it made a ARP request. So it's saying, whose IP 192.168.1.214, who is that? Who has that MAC address? And then it's saying, tell, me. Then the ARP reply comes back and says, oh, the IP address of 192.168.1.214 is at this MAC address. So this device has been allocated this IP address. This device's MAC address, again, is static. It does not change. It's unique to that device, whereas the IP address that's been assigned to it is a logical address that can change, and tomorrow I might be 2.15, 2.10, or I could be 2.14 again, but it's logical. So the request goes out. I'm broadcasting out to say, hey, whose MAC address is at this IP? And then the reply comes back to say, oh, 214 is at this device here. So when we're thinking about ARP, we're thinking about IP to MAC. Now going the other way, MAC to IP is reverse ARP. So reverse address resolution protocol is an obsolete protocol, not really used anymore, to map a device's MAC address to its corresponding IP address on a local network. It's primarily used in legacy environments where diskless workstations needed to obtain an IP address from a server without having a hard disk to store network configuration information. So what are you going to take away from this slide? You're going to know what ARP is and that it's IP to MAC address. The ARP protocol is going to be used to say whose MAC address is at this IP, and you'll resolve the computer's information that way to then be able to leverage the switch to say, I'm routing to this MAC address over there, and the switch will go out from layer 2 to layer 3 to the router to give it an IP address, to have the router route to the IP, and your data will start moving up the OSI model and being transported out. Another important slide that you probably want to memorize is the classes of IP addresses. So we have multiple ranges of IP addresses from A to E, and each basically denote a number of networks you can have assigned to them and a corresponding number of hosts. So you don't need to memorize verbatim what's in this, just kind of be aware that as the classes are assigned, A is going to be your largest class of IPs that you can have because it's going to have the largest number of hosts that you can have. And as you move down to class B, the amount of hosts that you can have go down and class C will be smaller. So why would you want to know the different forms of classes? Just to get a conceptual, understanding that if you have a class C network, maybe you're working with your home and you only have 254 or less devices that need to be assigned IP addresses. Whereas if you're working with class A or B, maybe you're working out of a big corporate building or a series of buildings that's all contained within your company's local area network, and you would be assigned a class A address over a class C address range to accommodate the number of hosts that need to connect out to the internet. That's really all you need to be aware of for classes and IP addresses. But this right here, this entire chart, you will need to memorize. You need to know what IP addresses are public and which ones are not public and are private. Knowing your private IP address ranges will help you tremendously because you will know that this is a non-routable packet. It's going to stay within that local area network, so within your home, within your corporate building, whatever LAN you have set up to communicate for devices solely within your local area network, they're going to use non-routable IP addresses. We're going to talk more about this later, but I would definitely be aware of all A, B, and C classes that you can have and the address ranges for which range applies to what class. And I would know your network prefix, so your CIDRs here. That class A is your 10 dot IPs, and it's going to have a HAC 8. Your class B is going to be 172.16 to 172.13. It's going to have a HAC 12 range, and your class C is going to be your 192.168 IPs, and it's going to have a HAC 16. Now, we're not going to go into subnetting or covering, network masks and allocations of hosts versus networks that you can make, but you need to be aware, basically, that your private IP addresses, they're not going to be able to communicate out over a WAN. You would need a public IP to communicate from one host to another host on a different LAN. So it would need to be at the router layer, a public IP that traverses the internet. If you have a private IP, it is non-routable. Non-routable, meaning it can't go through the router. It cannot route over the internet. It's only applicable to your local area network to stay within your LAN, and it will not route over the public internet. So any device that's within your company's organization or your home network will be divided into one of these three classes. It will have a private IP address allocated to them. You could have a combination of these, and all of your devices will fall within the prefixes here of the 10 dot, the 172.16, or the 192.168 IP range, and that is a very quick way for you to identify that that is a private IP address. It can't be routed. It must be local to a LAN, and it's not going to go out over a WAN or the public internet. Other addresses to note, starting with the loopback address. This is an address that is special reserved for devices to kind of communicate with themselves. And we use this for testing and troubleshooting. And right here, this is going to be your loopback address, your 127.0.0.1 for your IP version 4. And it will be : 1 for your IP version 6. I would definitely memorize both of these numbers. The loopback address will be an address that's available on every single device as it's internal to the device, as it's looping back just information on itself. and it's communicating with itself through this IP address. Now, this is not going to be used for anything else. This is a reserved address, and it's always going to be 127.0.0.1 or : 1. And just think of it for communicating with yourself on your own computer, and you can use for testing or troubleshooting network interfaces and applications. The APIPA address, this is your automatic private IP address, and it's a feature in Windows that will automatically assign a unique IP address to your computer if DHCP fails. DHCP is Discovery Host Configuration Protocol. We'll talk about that later in this mod. That's basically the service that's responsible for assigning your computer an IP address and leasing out a private non-routable IP to you. In the event that this service fails and it doesn't allocate an IP address to you, well, it will automatically assign an IP address to you in the range of 169.254.0.1 to 169.254.255.254. And again, only talking about LAN as it's a non-public IP. It is a private IP, not going to traverse the network, going to stay within your LAN. And if it can't get a 10.IP, a 172.16 to 172.32 IP, or if it can't get a 192.168 IP range, again, your private classes, you're going to know. If it fails to allocate one of the IPs in this ranges, you'll get your APIPA address for Windows. IP version 6, we're wrapping up here with a comparison for IP version 4 versus 6. And basically what happened was IP addresses only had a certain number of addresses available, and we ran out of IPs. So IP version 6 came out after version 4 to now make, instead of a 32-bit address, we now have a 128-bit IP address that can allow for virtually unlimited number of unique addresses to be applied, where we don't need to use public and private. Everyone can have a public IP and assign to their device. And again, we're slowly transitioning from IP version 4 to IP version 6 with the goal of obviously replacing IPv4 into IPv6 for dominant protocol of internet communications. The last slide here of the length comparison of version 4 IPs versus version 6 IPs. IP version 4 deployed out in 1981, and it didn't take us that long because in 1998 we realized that we ran out of IP addresses to give devices. The major comparisons that I would know, that IP version 4 is a 32-bit address. IP version 6, you're now having a 128-bit IP address. With this combination, so with your IP addresses for ranging from 0 to 255 at each octet, any combination of those four numbers you can have in each octet, that will give you 4.3 billion addresses. And since we have more devices on the internet, think about this as a global protocol that we're using as it is, there's more than 4.3 billion addresses. Think about the number of people that would need an IP address for their computer, their laptop, their phone, their TV, etc. Each person is using more than one IP address, so we very quickly ran out of the numbers that we can assign to each device, and we quickly exceeded 4.3. That's why we now have addresses that must be reused and masked, and we have, private IP ranges to share one publicly routable IP address for our home. So we'll get more into that later, but again, IP version 4 ran out of IP addresses, limited to 32-bit allocation, and only 4.3 billion addresses could be made. When we roll out IP version 6, we can now have 7.9 times 10 to the 28 available IP addresses, and every device can have a unique address. We don't need to worry about public or private. And this is an example of an alphanumeric hexadecimal notation of an IP address in IP version 6 versus what we're used to seeing over here in IP version 4. So you can shorthand notation this, but basically it's a new version of IP addressing that has come out that will solution our problem of having to use public and private IPs. We'll just use a public IP address for every person's phone, tablet, computer, laptop, whatever. All of those will have a unique IP address to them, kind of like a MAC address would be unique. We have enough MAC addresses to go around for all of our devices, and with IP version 6, now we can have enough IP addresses to go around for every device on the network globally. A good comparison here to wrap up section 2 of module 3, I'm comparing the importance of IP version 4 to IP version 6 and why we've made the switch.